Okay, so where we finished on Friday was with the idea of the discovery that light was an electromagnetic phenomenon, and that light in particular was made of these electric and magnetic fields that we had been using to describe electric and magnetic forces. And this discovery is usually considered to be, I guess the word you might use would be the culmination of what we call classical physics, physics up until the point of the end of the 19th century. It was a very, it was kind of a victory, if you will, for physics, where this discovery and this realization showing that light was electromagnetic in nature and that electric and magnetic fields were connected in this way, combine all these different fields of science into one larger field. Electricity, magnetism, optics were originally all separate fields of study. But then this discovery that light was a wave in the electric and magnetic fields combined them all into one thing. And at that point in time, there were many scientists, thinking that you were hitting the end of physics, which is kind of a crazy thing to say when you say it out loud in the modern day, that any scientific field could just end. You could just discover everything. But nonetheless, given the success of classical physics theory up until that point, you wouldn't really blame someone for saying that. However, as we got closer and into the beginning of the 20th century, we started being able to discover and see experimentally many situations in which the models of classical physics did not work correctly. And in particular, these models mostly focus on things that are moving very fast or things that are very small. So a little graph for you guys here. So this little box here shows the x-axis here is size from 0 to huge. So very quantitative graph here. And the speed on the vertical axis goes from 0 to the speed of light. And 19th century physics, which is mostly what we've been studying over the past year, fits into this little box here where we have things that aren't too small or too big. And they're also not moving very fast. And it is in this realm that mostly the theories and models that we describe work really well. If you get to things that are moving much faster, and the cutoff here is really about 10% of the speed of light, then all of a sudden the models we have stop working. What do I mean by that? I mean that, for instance, the formula we have for kinetic energy does not quite work to predict the energy of particles as you keep moving faster and faster and faster. It's only an approximation. And this is also true for our laws predicting forces and our laws for potential energies as we get very small. If we start considering, truly considering the atomic properties of electrons or protons in a nucleus, all of a sudden the simple force laws of force is equal to mass times acceleration doesn't work very well to describe the forces that are holding the nucleus together, for instance. So, conversely, also, we have things that are exceptionally big. They're exceptionally massive, like black holes at the center of the galaxy. Classical physics doesn't work really well to describe their properties either. So, over the course of the 20th century of physics, developing theories that two of which are associated with Einstein almost exclusively are special relativity and general relativity, and one that's associated with a whole combination of physicists and chemists, the physics of atomic physics and physics of subatomic particles, quantum mechanics. We're really building these new theories where it was the focus of physics in the 20th century. So over the next few classes, I'm going to give you just the barest bones introduction to a lot of these topics. And in particular today, what I'd like to do is focus on one experiment that shows us how our current models are not working. And this is often, if you've studied any of these subjects before, maybe in a chemistry class, if you're a chemistry major, you may have heard of this, but the experiment we're going to talk about today, and the experiment in your lab that I'm going to give you tomorrow will focus on, is called the photoelectric effect. So this, basically in words, what the photoelectric effect is, it's an experiment where we take a piece of metal and we shine light on it. And the energy in the light is absorbed by the electrons, which effectively gives them enough energy to escape the metal. And if you have the metal in vacuum, the electrons can use this energy to get off the surface and then go fly through space. So this is one possible way of knocking electrons loose from a metal. I'm going to just give you a few here to give you a bigger picture. I'm not going to quiz you on these different types, so don't worry about copying down every definition if you're taking notes in a notebook right now. But I just kind of want to put the photoelectric effect in bigger context. So the ways in which this can happen, other than using light to get an electron knocked off the surface of a metal, you can heat things up. That's called thermionic emission. So this takes electrons, and if you heat up the surface enough, you'll eventually give the electrons enough kinetic energy to escape the surface and jump off into the space around. Another way is called secondary emission. It's kind of a strange name, but basically what it means is that you more or less give electrons, instead of heating up a metal or hitting with light, you hit a surface with a very high energy particle. So you might take a particle from our cyclotron particle accelerator we talked about a few days ago and speed it up and hit a surface of a metal. And basically then it's, if you want to think about an atomic collision problem, you have this high-speed particle that hits all these electrons on the metal, transfers all the kinetic energy, and some of those electrons gain enough kinetic energy to escape the surface of the metal. Third way would be just using a static electric field, not one in a light wave, but one that's just not changing in space, maybe by using a battery or a capacitor or some sort of electric field source. You can create a strong static electric field that just physically creates a force and pulls the electrons off of the surface. And lastly, in this kind of range of different ways to knock electrons off the surface of a metal, the photoelectric effect fits in, where we do this with light. So instead of hitting electrons with a particle, we shine light on a material, and light gives the electrons the energy, allowing them to escape. So the idea, hopefully the idea itself isn't very complicated here. Hit electrons with something to give them energy. That energy allows them to escape the metal. The tricky and confusing thing comes in, or at least did for scientists who first started studying this, when they tried to figure out exactly how much light you would need to knock off a certain number of electrons. And it's trying to predict this experiment and model it and fit the graphs for the experiment that led us to realize that the models of classical physics really don't describe this possibility well. You have to add in new ideas to the model to get good results from this experiment. So let's see what like an experiment like this could look like in practice. Obviously, it's not just like, here we have just a picture of a cartoon, but let's make it a little bit more scientific. So cartoon is still in the upper corner there, but this is what something like this experiment would actually look like in like a very simple circuit diagram here. So down here we have some ends of our wires where we would attach a power supply, possibly a battery, but in practicality, some type of adjustable voltage power supply, so we could change the current. We'd have some wires that would then connect to two metal plates, one we call the emitter, one we call the collector. On the emitter, we want to have a lot of extra electrons on there, so we're going to make that, the more extra electrons on there, the bigger this effect will get. So this will be our negative side. Over here, the collector will be our positive side. The free electrons will then, once they're free, will travel and be pulled to the positive side. And that will create a current through the wire. Even though the wire isn't physically connected, these two plates are inside of a vacuum tube. Once the electrons are free, they're able to jump from emitter to collector and complete the circuit, giving us a current, which we can measure with a meter in the circuit here. Current meters are called ammeters. So that's kind of what's going on here. The vacuum tube is needed because if there's air in here, electrons are going to hit atoms in the gas around the plates and never make it to the collector. So this experiment has to be done in a vacuum tube. Usually it's a glass vacuum tube, so of course we can take our incident light and light can shine through and hit the surface. So is that clear to anyone? Does anyone have any questions about any of these different parts in the experiment? Main takeaways: we need a current meter, a voltage source, and the metal that's giving off our electrons is over here called the emitter. So in effect, what we have is a really highly charged capacitor, and the light allows electrons to jump the gap. Okay, so let's say now our experiment is going to be, we have light, we have a lot of free parameters we could change here. We could change the voltage, we could change the wavelength of the light, we could change the intensity of the light, how much light we shine on the emitter plate. And we want to do an experiment that kind of graphs these things, shows us how many electrons do we get for different situations. The first observations for this experiment, before I show you the graph, were originally made by Heinrich Hertz, who we know and love because our frequency unit is named after him. But he originally did this experiment, or did the initial observations. And it's worth pointing out what he expected to see. So classical theory, classical physics, 19th century physics, predicted that the electrons absorb energy from the beam of light at a fixed rate. Doesn't really matter. So if you have really low light intensities, so really dim light bulb, shining light in this metal, it would take a long time for an electron to get energy. It'd have to sit there in the wave of light, slowly picking up energy. But then after a long time, eventually it would have enough and it would escape. That's what people were expecting. And based on the physics we've learned over the past year, it's what you should expect too. Hopefully it seems like straightforward for what you know about energy. However, the problem here is that no matter how dim Professor Hertz made the light, electrons were emitted almost instantly. And it didn't seem to depend at all on how strong the light bulb was. So it didn't depend at all on the intensity. So this completely, there's a complete disagreement with the theory that has worked very well in other aspects of science, and now all of a sudden is not working here at all in this one simple experiment. So generally what you can do is, as a scientist, in situations like this, you have to go back and look at your model. No matter how well it's worked before in the past, you're hitting a situation where your model is starting to break down. And remembering that no model is perfect and every model is going to need to be updated or improved or expanded upon in some situation is always something you have to keep in mind. Science is about building accurate, more and more, better and better models based off more and more data. So that's no matter how intuitive or comfortable or our models that we have are, no matter how well they worked, we always have to go back and question them. It's kind of the lesson of science, and it's especially relevant here in this discovery. So again, last thing there, as I mentioned, Obviously, this guy also did a lot of other things. In particular, discovered radio waves, which was really proof that light was an electromagnetic wave. Discovering light that we couldn't see at a different frequency was key to that. So this guy was important in many other ways as well. So let's see what he saw in this experiment, though. So here, the wave model of light predicts that as the intensity goes up, the kinetic energy the light gives the electrons should go up. Shouldn't depend all on the light frequency or its wavelength. And this is in particular what Heinrich Hertz saw, and what other people who followed the experiments did, is that the kinetic energy of the electrons depended only on the frequency. It's like the exact opposite of what you would expect. So if we kind of graph the results here, and this is obviously not the original graph of the original experiments, but it shows you what they look like. Depending on the metal you take here, what you see is something like this. So on the y-axis, we have the kinetic energy of the released electrons. On the x-axis, we have the frequency of the light. So what we see is that no matter the metal, whether it's lithium, silver, there are, at low frequencies, there are points where there's no electrons emitted. So the electrons come out with zero kinetic energy at best. So those would be points in this region. The dotted lines here aren't actual data, they're just, obviously you can't have negative kinetic energy, but they just continue on the lines from the graph. However, for every metal that this experiment is done with, you get to a certain frequency where all of a sudden you start getting instantaneous electron emission. And those are the points here, here, and here. This graph is from a book that uses a curly V for frequency. So this here, you might call this frequency F naught if we use our book. Hopefully that will be clear to everyone. I think I may have updated this on the slide and it's just not appearing. Oh well. So what we see here, we kind of like describe this graph in words. One is that the number of the electrons that we get out is proportional to how intense the light is, but the actual energy of any one electron was not. And this is in particular the thing that doesn't make sense based on our normal unmodified wave model of light. And this frequency we'll see on the next slide is an important parameter, the frequency at which electrons start being emitted instantaneously. It's where this line starts, and we're going to use the symbol F naught for it. It's called the threshold frequency. And that'll be written out in the next slide, I believe. Yep. So here, these threshold frequencies were also something that classical physics could not predict, or did not predict. Because remember, what we would expect is that for really, we would expect that there isn't really a dependence on frequency at all. You should be able to get electrons to be emitted whether you're using red light or blue light. There are wave oscillations that should jostle the electrons about. But it seemed that there's something about how electrons absorb this energy that is different from what we expect. The electrons don't seem to be as good at absorbing the energy for low frequency light. And it seems in particular to depend on the metal the electrons are in. So there's a lot of kind of interesting unanswered questions here. For all metals, the amount of electrons you get, as I said on the last slide, is proportional to the frequency, or the amount of electrons we get is proportional to the intensity of light. But the kinetic energy of any one electron, which is what's plotted on this graph here, is not proportional to intensity, it's proportional to frequency. So the fact that these graphs are linear and really linear is something that classical theory does not predict. So these are all questions we now have to answer. The slope in these experiments we use the letter h for that. So, but in particular, so this linear slope and these threshold frequencies that are bigger than 0 are something we can't yet explain with the physics we have now. So the question of what's going on here is the one we need to answer. So things we need to explain. Why is this linear? Why do these threshold frequencies exist above 0? Why do low frequencies not eject any electrons, even if we wait a long time? So that's our goal for today. Before we get there, though, what I want to do is we're going to introduce a new unit of energy here that we haven't used yet. Just because as we talk about atomic particles, the energies that we use are much smaller than what we're used to using for cars or trucks rolling down hills. And the unit of a joule for energy is really built for that kind of context. A joule has energy in units of joules has a reasonable normal amount if we have a car rolling down a street at a everyday speed. However, if we have an electron being emitted from a metal, its mass is so much lighter than a car. Trillions of times, 31 orders of magnitude lighter. And even more than that. So the units of energy for electrons are really around the order of 10 to the minus 19 joules. And it's an annoying factor of 10 to carry around in every problem. So we're going to find this new unit of energy, which you may have seen in some chemistry courses at some point, depending on your background. It's called the electron volt, and its symbol is EV. It's a kind of confusing name for a unit because it's obviously similar to the volt, which is a unit for potential, which is proportional to potential energy, but it's not the same. So here, the electron volt is a unit of energy, either kinetic or potential energy. And the conversion to joules is here in red. So this EV is kind of one symbol. So you'll notice the convenient factor here is that the conversion between joules and electron volts is numerically the same as the charge of the electron. So that makes it kind of easier to remember, same number. But you might want to keep this handy for problems later on because this conversion will happen again and again. Does anyone have any questions on this? In particular, it's just a new unit of energy. One that will have a more reasonable numerical value for the problems we're going to do. Okay, so with that energy unit in mind, let's discuss conceptually what the solution to this problem is with the photoelectric effect. So it was Albert Einstein who came up with the modification that allowed us to get a good description of these experimental results. So it's worth pointing out that this suggestion is completely contrary to a century of observations for light. Yet that didn't really stop Einstein. So what he said was that the energy in light is somehow contained into chunks. And those chunks have a particular size. And the word we use for that is that they are quantized. So these chunks we now call photons. And every light wave, no matter its frequency, its intensity, the energy it contains is made up of these different chunks. And these particular energy can be added to the wave or taken away from the wave, but it can only be done so in units of these chunks. You can't add half of a chunk or half of a photon of light. If you wanted to increase the energy of a wave, you could add 1 photon, 2 photons, 3 photons worth of energy, but you can't add in like half or 1/8 of a photon. So these are often called particles of light uh, in modern terminology, but really the key thing for how this affects the experiment is that, for now, I'd like you to think of light as a wave, but the energy we add or subtract from that wave can only be done so in terms of chunks. So these are chunks or quantities of energy of light. The other thing, the mathematical statement of this is that the size of these quantized units of energy depend on the frequency of the wave of light. So blue light, for instance, has larger chunks of energy than a red light wave. So the energy contained in 1 unit, 1 photon of light energy, is proportional to the frequency. That the constant proportionality here, h, conveniently the same symbol as the slope in our graph, as you'll see in a second, that is not an accident. This constant of proportionality h is named after Max Planck, and it's called Planck's constant. And I give it to you here in both. The units of Planck's constant convert frequency to energy. So the units are energy times second. And I give it to you here in both units with energy as joules and energy as EV, electron volts. So depending on the units you get in your problems, you want to have both of these on hand. But the main conceptual idea that fixes the problem with describing this experiment is that our light waves, we can only add or absorb energy from a light wave in certain units of chunks. If the energy we need is we can't absorb half of these quantized units of energy, we can't absorb 3/4. We have to absorb 1 or 2 or 3, so on and so forth. So any questions about the conceptual idea before we go back to the graph? All right, so one last word is that if you wanted to know the total energy in a light wave, you'd have to know how many photons were in it, and then you could multiply this energy of 1 photon by that number to get the total energy of the light wave, if you wanted to think about it like that. So the reason why this helps our experiment is when we go back and we think about what the electron's kinetic energy is in this whole situation. So let's think of our electron that is absorbing energy from the light wave. Effectively, the kinetic energy after it breaks free from that metal surface is going to be equal to whatever energy was in that photon minus the potential energy we needed to escape. So that potential energy is, in this problem, is written, at least in our book, we use the symbol E naught. And in this context, it's called the work function. You may think of the name comes from how much work you have to do to break that electron free. But more or less, it's a measure of the potential energy holding the electron to the surface of the metal. The new thing here, so really the idea of kinetic and potential energy is exactly the same as before. The only new thing is that now the energy the light is giving the electrons is now proportional to frequency due to this photon model that Einstein proposed. And it gives us this linear relationship between electron kinetic energy and light frequency. So just by using this model of light energy being quantized, being broken up into these chunks, we get our linear relationship. So one of our problems is solved. So let's see how we can predict these threshold frequencies now. So that all comes in from looking at this E naught, this work function or the potential energy that we need to overcome. So here, notice that of course should hopefully be sensible to you guys that depending on the metal the electron is in, the potential energy you need to overcome to knock an electron loose is going to be different. So for instance here, potassium is a lower value. Here all these values are in electron volts, not joules. Gold here is the highest value on our list, about a little over 2 times bigger. So numerically, it's hard to see why the metals are arranged in this order just from the information I'm giving you. But hopefully it's understandable that different metals, the electrons will have different potential energies that you need to overcome to break them free. And it really comes down to how strongly things are bound in that particular metal. So here, let's consider the maximum amount of kinetic energy that we might be able to give an electron when we hit it with some light. So this maximum kinetic energy is going to be equal to the energy given to the electron by that photon of light that it absorbed. So here, HF minus the work function. So taking our equation from the last slide. If we wanted to actually measure this, what we can imagine doing in our experiment is applying a voltage to slow down the electrons that are released. So this is something we're doing experimentally. And this voltage, whatever it is, the voltage, the smallest voltage we need to completely stop the current in the circuit, this is going to be proportional to whatever the maximum kinetic energy we have. So here, this is an experimental relationship where if we want to figure out what voltage we need to stop all of those electrons in the circuit, we need to take this maximum kinetic energy the electrons will have and divide by the charge on the electron. And we could use our energy relationship from before to get that. So let me briefly just go back and show you what we're doing in the experiment here. So going back to our picture of the experiment, we have our light coming in. Light is absorbing, or the electrons are absorbing the photons from the light. They're traveling outward, going to this collector, and making a current in the circuit. If we take our power supply and make the voltage positive as we had it before, we'll attract electrons to the collector plate, help the process along. However, even if this voltage here was 0, if we're releasing these electrons, some electrons are going to make it across the gap, and we're going to get a current in the circuit. So this voltage isn't necessarily necessary as long as we have light hitting the metal that the electrons can absorb. So the light is kind of acting as one energy source. We could then use this power supply to apply a reverse voltage to slow all these electrons down. If we find the smallest voltage to slow and stop all these electrons from getting to the collector plate, that voltage is the voltage that we are calling the stopping voltage on this slide. So this in particular, by applying this voltage, figuring out what it is, and then converting to kinetic energy, this is how we actually get a measure of the kinetic energy of the electrons released. So looking at this experiment here, so we can apply this stopping voltage and watch the current in the circuit. And what we see is that if we apply positive voltages, we don't affect the current all that much. We only have so many electrons being released by the light hitting the plate. So we can apply this voltage, but the current doesn't increase. So this is clearly a system that doesn't follow Ohm's law. However, if we start applying a negative voltage, we start slowing those electrons down, and we slowly but surely decrease the current. And that we can see here. So we start at some maximum value I naught and decrease till eventually our current is 0. This voltage here at this point, that is our stopping voltage. And the reason it's negative is because it needs to be in the direction to stop current flow. So that's what the negative sign means here. So we have some electrons come out. Obviously, statistically, some absorb more photons from the light, some absorb less. So the actual difference, there's a distribution in energy for the electrons statistically. So we apply a negative voltage. Some of the electrons will stop, but not all. But eventually, there's a voltage where we stop them all. And that voltage is proportional to the maximum kinetic energy of the electrons released, as predicted on the last slide. So these are the properties of this experiment, and the properties that the problems from the next problem set are going to ask you about. So we'll do a few quick examples. These problems tend to be a bit more straightforward, and I think hopefully easier to learn online. So hopefully it's a bit more straightforward than magnetism. But one last thing I want to mention about the experiment before we do some problems is just if we go back to this graph, the presence of this potential energy function, E naught, the potential energy of the metals themselves, and the potential energy we need to overcome to break the electrons free, that's what gives rise to these different threshold frequencies. So the more strongly the electrons are bound in the metal, the more energy you need to give the electrons to break them free. And thus, since the energy is proportional, energy the electrons absorb is now proportional to frequency, that means for certain frequencies that are too low, where the photons don't provide enough energy to the electrons, we won't have any electrons released from the plate. So that was the last thing we needed to explain. And I want to highlight here that this linear relationship we built with this one assumption about light energy being quantized explains that as well. So if there aren't any questions about the theory here, we'll do our first problem. These will go pretty quickly. I know we're nearing the end, but so any questions? All right. So let me walk you through one of these problems since we're running a little low on time. I'll kind of show you how these work. So here we're going to take two metals, sodium and aluminum, and we want to compute what the threshold frequencies for electron emission are. So these are those minimum frequencies minimum frequencies of light that will start emitting electrons. And basically what this means is that these are the frequencies that will knock the electrons loose, but will knock them loose with basically zero kinetic energy, or kinetic energy that's just above 0. So we give them just enough energy to escape, and then no more. So if you want to find these threshold frequencies, this is the assumption you need to make. Set the kinetic energy of the electrons after they're knocked free equal to 0. Here I'll work in joules, just for the sake of using the units we always work with. So here, what this means is that the kinetic energy of our electron is 0. So the energy of the photon the electron absorbed minus the work function, the potential energy we need to overcome, has to equal 0. So we could plug in our formula for the energy of the photon, and if we solve for the frequency here, that will give us the threshold frequencies for these two metals. We just have to plug in the correct work function for that particular metal and solve for F. So here, the mathematics here is quite straightforward. So it's work function from the metal, which we can look up on the table from the last slide. And we'll use H in Planck's constant H in units of joules times seconds. So I'll leave it for you guys to fill in the gaps here, actually plug through these numbers, but the algebra here for these problems is much more straightforward. So I'm confident you guys can all do this without me going through it in much detail. But you'll be asked on a few of your problems to look for things like the threshold frequency. So remember from this problem, finding the threshold frequency means the frequency that will give the electron 0 kinetic energy right after they escape the metal. In terms of wavelength here, just so we know what we're talking about in some other units, these frequencies for visible light and UV frequencies are around 10 to the 14 hertz. So here for sodium, the threshold frequency is around 452 nanometers in wavelength. That's very blue light. It's something we could still see. For aluminum, the threshold frequency is 290 nanometers, which is not something we can see. It's much higher frequency. It's in the UV range. So this experiment is something that we can, with some metals, we can do with visible light, but with other metals, we really need UV light to do this. Another example here might be applying this, this idea to other types of molecules. So it's not just metals that absorb light in chunks of photons, it's every type of molecule that's out there. So for instance, you may know that there are certain types of radiation that can, or certain types of light or radiation that can damage DNA molecules and others that don't. And it has a lot to do with this idea of how much energy there is in one photon of that light. So for instance here, this is all explained, this explains why UV radiation can damage DNA, lead to skin cancer, for instance, but infrared radiation or visible light does not. It's because of the size of the energy in the photons. So each molecule of DNA in our skin cells, for instance, can only absorb energy from light in units of these individual photons. So there has to be enough energy in one photon, really, to cause damage. If there isn't, then that particular color or frequency of light will not cause damage to one individual DNA molecule. So for instance, for red light here, now I'll work in units of EV of electron volts to give you some idea of how they correspond. So here, all I had to do is now I'm using Planck's constant in units of EV. That's the only difference here. Frequency is still in hertz. So red light has energy of around 2 electron volts in those units. UV light, however, is around the same order of magnitude, but now around 5 electron volts. And that's what makes the difference here. Those 5 electron volts end up being enough kinetic energy to damage or break a DNA molecule in a cell. 2 electron volts is not. And that is in particular why the chunks here are over twice, the chunks of energy that the molecules can absorb are over twice as big. And so the chunks of energy in red light are not enough to really break bonds in DNA and cause damage. But in UV photons, they can. again, here, this example, the algebra and mathematics is significantly lighter than the past few chapters, which is hopefully a nice break for you guys. And I think it's a little bit easier to get. So hopefully the problems are problems that will hopefully go a little bit quicker this time around for you guys. And lastly, we're at the end of class, so I had a few more problems with graphs, but the next ones don't really relate to the problems that you have assigned. The problems for today, there are going to be 4 of them. They all relate to calculating different things in the photoelectric effect experiment, threshold frequencies, what the work function must be, the final kinetic energy of the electrons. So all of the problems relate to using the 3 equations from these slides. In particular, this equation for the energy of the photon of different colors of light, combined with the equation for the energies in the photoelectric effect experiment. There are 4 problems. Don't think they should take all that long. Your lab this week will be looking at a simulation of this experiment, and that will be posted tomorrow. So if you don't have any questions, that's the end of class for today. Thanks for listening, and I'll see you guys Wednesday. I'll hang out for a bit if any of you do have questions, though.